Hi, in this video we'll be talking about moving averages. Moving averages are some of the core foundational concept of time series analysis, and in this video we'll be talking in detail about moving averages, the various moving averages type. You have your simple moving average, you have your weighted moving average, you have your exponential moving average and exponential smoothing moving average. We will be talking in detail with examples on all these four cases. Now, when it comes to moving average forms your baseline model for time series analysis. Now, this is not only used in time series analysis, this is also used in your typical machine learning model. It can be your RFM model, that is the recency frequency, the monetary benefit value, with where you can use to calculate features on various time duration of your customer. It can be how frequently the customer visited you, or how many times did he visited you in the last 30 days, 60 days, 90 days. It is also used in behavioral models to detect next best action. So if you want to analyze your customer history to see what is the next best action, you can use your the moving averages function as features in your machine learning model. I'll be talking about it, but the core concept of weighted averages is used across multiple analytics domain. If you take the streaming analytics, a lot of the streaming analytics window functions are coming from your typical moving averages. So we are going to see in detail. Now, one of the core assumption of moving average is basically your time series is stationary, and also it has a very slow varying mean. Now, if your data has a lot of fluctuations, if your data is non-stationary, if your data has non-stationary mean, then maybe the moving averages might not be the best method to basically do a forecasting. But said that, like, if your data is pretty stationary and it has a pretty constant mean, then you can use this weighted moving averages. Now, for this purpose, what I'm going to do is I'm going to take a data set which is not stationary, just to show you how various moving averages react to it. Because if I take a stationary data, then all the moving average might look similar. So I'm going to take a non-stationary data, and I'm going to show you like how it performs against this non-stationary data. So let's get started. So what I'm doing is I am importing the typical matplotlib library to do the visualization. I have my NumPy library. I'm going to use this to calculate the RMSE manually. And then I have the pandas library where I'm going to load the data set and do the analysis. I'm just setting these two parameters so that I can visualize my data better. But I'm just setting like figure size so that it show me in a 10 to 8 grid, right? So the very first thing I'm doing is I am reading the data set from my GitHub repo. The data set is available in my GitHub repo in this link. You can go and download it. It is a electricity consumption data set. This electricity consumption data set is a data set of electricity consumption in my house from 2016 to 2020 latest month. So this contains like the amount that I am paying for electricity every month over time. Right, this is a data set I'm going to use, and one of the column in the data set is the date. So what I'm doing is I'm telling basically the bill date column is the date function because your time series is ordered by date time. So I'm telling is the date, and then once you encounter this date, call this parse function. This parse function is on the top, where I am just taking this and converting into an month, day, year format, so that the data frame registered is as a date time data type rather than a string data type. That's the main purpose of it. So let me run this, and let's see the output. Now this data set has a bill date column, which I said like is a date time column, and the data is ordered by bill date. All right, and then I have build amount column which I'm going to use for this analysis. This is the only column I'm going to use, but there are other column as well. This on peak and off peak is basically the kilowatts that I am using every month. So the way my bill is basically I have an on peak charge and off peak charge. If I put my heavy appliances during the off peak, then I'm paying very less on my electricity bill. But if I use these appliances on my on peak, I am at least paying 3 times the regular electricity charge. So that's the on peak and off peak, and this constitutes to the bill amount, right? So I'm going to use bill amount as I said to you. So let's quickly visualize this particular data set. How many rows are there? How many columns are there? And everything. So yeah, what I'm printing is I'm printing the number of rows first. There are 53 rows and 6 columns. These are the 6 columns. There's no missing value. I just printed like df.null.any, so it's going to give me all the missing value, as there's no missing value in this particular data set. Now, in case of missing value in time series, you cannot handle it in like your regular machine learning model. So I have a separate video covering missing value. In case if you are not seen that, you can click the link on the top and watch it. I talk about various techniques of handling missing value, like forward fill, backward fill, date offset fill, or the rolling window fill. You can click the link on the top and watch it. But here it does not have any missing value, and I am printing the unique value, right? The very first thing I'm doing is I am taking the data frame, I am setting build date as the index column. The reason I am setting in index column is, first is, a lot of your plotting function or a lot of your statistical techniques to analyze time series want this as an index function. The second reason is creating it as an index makes my analysis easy. Now, where if I don't create as index, I have to do an exact string search. But with index, I can do substring search and I can do partial string search. So that's the reason I'm doing a set index, and I'm assigning it to a bill underscore df data frame. Let me run this and let's quickly visualize the final data frame. And if you see over here, the bill date column is the index now, and all the other columns are on the top. So if it is not an index, then bill date will also come in the same level of other column, but bill date is an index now. Now from this particular data set, what I am doing is I am just taking the build amount column. Since build date is an index, it will automatically come, and I am taking only the build amount column, and I am taking from between year 2016 to 2018. So this is what I said, right? If in general, if I am going to go and search for a column, I need to use the exact string match 2016 01010201. But with the index column, I can just do a partial search, and that's what I'm doing over here. I'm telling between 2016 to 2018 get the data, and assign it to a new data frame bill underscore 2018. Now this will have 3 years of data, that is 36 data point. So let me quickly run this, and you can see it has only one column, the bill amount. Right now, what I'm going to do is I'm going to take this build amount column, and I'm going to run various moving averages function to see how it performs, how it is able to predict the output. Right, this may not be the perfect model, but it's always a good model to start with, a baseline model, so that you get understanding of your baseline performance. And in this case, my data is not stationary, so maybe it does not perform great, but let's still see how it performs. Maybe we may find a good model as well, we don't know. Right, so it has 36 data point. The very first thing I'm going to do is simple moving average. Now, simple moving average calculates an average of the last n data points, right? Where the n in this case represent the number of period for which we want to average. So simple average is nothing but the typical average you do, the typical mean you do, right? That's what it is. Now what I'm doing is, here, if you see the formula, I'm taking the value at t, I'm taking the previous value t minus 1, t minus 2 until t minus n, and then dividing it by n. Now this data point, how much data point you want to take, whether 1, 2 or 3, is also called window function. So what is the time window you want to pick the data of, right? And that's what we are going to do now. Now we have a very handy function in pandas to calculate simple moving average. It's called the rolling function, right? So what I'm doing here is I'm taking the data frame, I'm taking the build amount column, I'm doing a rolling over here, I'm telling window 3. Now window 3 is the n, right? In this case, I'm telling pick for 3 data points. So current data point plus the previous 2 data points is what I am asking to pick for, and then I'm calculating the mean out of it. That is simple moving average. Now, if you see the output, basically I get all the data points over here. Right now, what I'm going to do is I'm going to put it next to my build amount column and see how the prediction has been. Right, this is just a simple moving average. We'll go to more complex functions like exponential moving average as we go down the line. Now, here what I'm doing is I'm taking the bill underscore 2018 build amount, the same function on top. I'm just using one additional function called shift of 1. The reason I'm using shift of 1 is basically I'm taking the current value and previous two value and predicting the next value. So the shift will shift to output from one time frame. Right, so instead, if I'm taking the March data, I'm taking the March data plus the Feb and Jan data to calculate the rolling window, and that will be my April prediction. So I need to shift the output by one data point. You can see the output, and I'll just quickly show you the output. I am assigning it to a new column called MA moving average underscore rolling 3. So let me run this and let me show you the output. Now you have two columns, not only the build amount, but you also have the rolling three. And you can see the first three columns are null because I have given the window function of three. The first two will be empty, but the third one is empty because I did a shift function, right? So the first three are empty, but you can see like, okay, if in this case it's 111, it predicted 201. The initial will be wrong because that is the initial one. But as you come down, let's see how the prediction is. Still 290, 222, still decent enough, 257, 264. But there's a sudden variation over here, 327, and this only 277. The reason is moving average is pretty flat. It does not give any advantage to you on the latest data point. The sudden surge might not be detected. So that's the reason like moving average might not be a great tool when you have non-stationary data or data that has a lot of fluctuations, right? So this is the output. But right now what I'm going to do is I'm going to plot it and let's see how it performs. Now if you see the blue line basically here is your build amount, that is the actual ground truth, and then your orange line is basically your rolling three. And if you see the output, even though it's not like closer, not that close, we will finally calculate the RMSE and see how each and every model performs. But it's able to capture the fluctuations, the ups and downs. It's able to capture basically the maybe there's a seasonality. It may be able to capture the seasonality, but there's a time lag that it may capture the seasonality, the moving averages. Right? So that is about moving average. The next one we are going to talk about is weighted moving average. Now, if you see the moving average, they just took the previous three data point and directly averaged it. But what weighted moving average is, it gives you a weighted average of the last 10 data points where the weightage is what you assign. So the weightage, basically, what you can do is you can tell, okay, for the latest data points, put a higher weightage when you are scoring the output. For the previous data point, we put a lower weightage, or it can be other way also. For the previous data point, you can give an higher weightage, and the current data point, you can give a lower weightage. And why do you want to do that, right? Think about it. Like when you are doing an RFM analysis, right? The recency and frequency of visit of customer. If a customer has visited you 3 months back, the probability of him visiting may be less than the customer who was visited you last week. So when you're calculating your averages across multiple customer, you may want to weight the latest data point to understand what is his next probability of visit. Right now, one thing you have to keep in mind is the weighted moving average is generally more sensitive to your sensitive to your data points. Right now, this can be a double-edged sword sometimes. Right, on one side, the weighted moving average can identify trends sooner than a SMA. Right, your simple moving averages, but on other end, there's a complexity as well because you need to assign the weights manually. But when you go exponential moving averages, yeah, that shortcoming is overcome, right? But let's first see how to do it. Now this is the formula for it. So what you are doing is you are taking the time period t, that can be your current time period. You are multiplying it with the weighting factor. The weighting factor is you are going to assign, right? Or I'm going to assign in the next step the t minus 1, and I'm giving a weighting factor, and t minus n weighting factor by n is the same formula. The only thing is with each time point I am multiplying a weight factor. That's what I'm doing. Now, what if you see the weight factor is nothing but is this NP array that I have given over here. So I have given weight factor as 0.5, 1.5. So to the latest data point, I'm telling assign 1.5 weight factor, and to the old data point, I'm telling assign 0.5 weight factor, right? And I have given this should add up to the window size. If it's not adding up to the window size, and you can also add up to 1, in that case you don't have to do the mean in the formula, right? But for now, just add it up to your window size, right? So what I'm doing, first I'm creating a function. Now pandas does not have an inbuilt function for this. There is a function in numpy which you can use, but it's little complex, so I thought I will create a function. Creating a function is simple, right? So I'm creating a function over here called WMA. I am passing the weights. The weights are nothing but the NP array that I am passing to it. And then I'm creating an inner function where I'm doing the calculation. And it is taking X as input. The X is nothing but the build amount column that I'll be passing in using the apply function, right? And then what I'm doing is I'm taking the weights into the X value. So I have the build amount column. I will have window function. My window is 3 over here. So I will have t minus 1 and t minus 2. And then with that, I am multiplying 0.5, 1 and 1.5. and then I am getting a mean. That's what I'm doing over here. So let me run this, and let me run this. You can see the output. So if you see over here, this is the output I get. Now what I'm doing is I'm doing the same thing. I'm doing a rolling window of 3, but instead of calling the mean as in weighted average, I'm calling an apply function. I'm calling the WMA function I created on top, and I'm passing the weights, and this is the output. Right now, let me concatenate with the pandas data frame so that we can see how it perform. So what I'm doing is I'm again taking the same function. I am doing a shift of 1 as I did earlier, and I am assigning it to a variable called WMA rolling 3. Right. So let me assign here, and let's see the output now. Now I have three columns. One is the actual value billed amount. Next is the next is the moving average, and third is the weighted moving average. Now if you see, basically it's 111, it's 181, 118, 135. It is little closer to your data point, no, not so far away as your moving averages, so it is performing slightly better, right? But again, there are a lot of data point, I don't want to go to individually, but what we will do is when I'm calculating the RMSC, you can see what is the error of each of every function. The next best thing we are going to see it, visualize it, right? Now I have all the three plots. I have the build amount, which is my blue line. I have my moving average, which is my orange line, and I have my weighted moving average, which is my green line that I created now. Now, if you see the weighted moving average, the green line is little better than the orange line because it is closer to the blue line than the orange line. In the sense, like orange line is further far away, right? And you can see basically it moves along with the blue line closer. So definitely the error will be lesser than the orange line, right? So that's where the weighted moving average come into play. Right. Finally, let's evaluate how it performed. But for now, let's keep continuing with the different moving averages. The next one I'm going to talk about is the exponential moving average. Now, exponential moving average is similar to your weighted average, but we don't assign weights here, right? So what it's going to do is it's going to take the previous time period. It's going to calculate the exponential moving average and then take the exponential moving average as the next input rather than the time t minus 1 and t minus 2. That's what it does. So basically, exponential moving average, the advantage is it adopts more quickly to your data point changes than your simple moving average, and it also has less headache of deciding the way of basically you don't have to decide the weights before itself, right? Like we did in the weighted moving average, it will take care of the weights internally by averaging it out. That's what it's going to do over here, and this is the formula. It has the final price, that is the last t value minus the previous EMA values. See here, here we are comparing the previous exponential moving average. So as it goes down, the exponential moving average output is cascaded, and that's why you will get a more smoothing effect than your weighted moving average. And then I'm multiplying by 2 by span plus 1. So this span is nothing but the duration that you want to calculate for. Now if you are from the stock market, right, you may see they publish like 20-day moving average, 30-day moving average, 40-day moving average, which is nothing but your simple moving average that we did first. Then they also publish your exponential moving average. The difference between your moving average and exponential moving average is the exponential moving average is able to weight the current events better, because that's what you want in a stock market. If I am calculating a 200-day moving average and my stock was completely beaten down 50 days back, and I take an average, then it will take all points equally, but I don't want that. With exponential moving average, my latest points are weighted better, and that's what a weighted moving average is, and that's what it does over here, right? So this span is nothing but, if I am calculating a 20-day EMA exponential moving average, then the span is 20. If I am calculating a 200-day EMA, then my span is 200. Span is nothing but similar to your window. What is the duration you want to calculate your EMA for? And then you are adding the previous EMA. Now, what I'm going to do is, in this case, I have a function called EWM in pandas, exponential weighted moving average, right? There's a function, it is that. And here what I'm doing is I'm telling my span is 3. That means I want to calculate my 3-day exponential moving average. And what I'm telling is the minimum periods is 0. So I can give minimum period 1. If I don't have 3 periods in the past, it will take minimum period, but I'm ignoring it over here. I'm calculating the mean. So if you see the output over here, this EWM function takes care of it. You don't have to manually code it. This is a very handy function. So now if you see, you get the output over here, right? Now what I'm going to do is I'm going to again put it to the data frame like I did for other two. I'm creating a new variable called EWM underscore window 3, and then I am basically applying this function which I showed you on the top, and I'm shifting by one as I did for other. So let me run this and let me see the output now. Now, if you see, I have one additional column over here called exponential window average. And now, if you just come down, let's see how it performs. Here, the value is 202. This is 206. This is also 206. But the weighted moving average for 215, right? Now it's 150. It's 204, which is closer to 150 than 213 and 223. Right now, 163 is close. 177 is closer to 163 than one. So it's performing a little better. But how much better we don't know because we are not calculated the metric set, which will come to that sooner, right? So what I'm going to do is I'm just going to quickly plot it. Now, if you see the plot, I have all other values as you saw. A new red line has come in, which is nothing but the exponential moving average. And then the exponential moving average, basically you can see the red line, sometimes the green line is better, which is your weighted moving average. But in some cases, you can see the red moving, if you see this area, the weighted moving average is slightly higher. The red line, that is the exponential weighted average, is closer to your blue line, right? So there is fluctuation. There are some points where your weighted moving average is performing better. There are some points where your exponential moving average is performing better. But let's wait till we calculate the final RMSE, right? The final one I want to talk about is exponential smoothing averages. Now, if you see on the previous one, we did not do anything. The exponential weighted average calculated by itself. But the exponential smoothing average, it requires an additional parameter called alpha, right? And this alpha is called smoothing factor or smoothing coefficient. Now, this parameter controls the rate at which we influence the operation, we influence the observations at prior time steps, and it allows you to decay those values exponentially. I'm going to show you what it is. Now, this alpha is often like a value between 0 to 1. The larger value of alpha means that model is paying attention mainly to the most recent data points, right? And then the smaller value means it is taking history into account. That's what it is. Now, if you see the formula, this is the formula. You see the alpha, this is the smoothing function or smoothing coefficient. Now, if you take the formula, you have y of t, then plus you have a smoothing factor, you have y of t minus 1, then you have a smoothing factor square, y of t minus 2. So this is where the exponential decay is happening, right? And then you have an y of t minus 3, you have a cubic function. So if you see, the alpha is basically controlling the smoothing decay over time, right? That's what it is. Now, for this, it's the same Fandas function EWM, but instead of the span parameter, I'm going to use the alpha parameter. The alpha parameter is nothing but the smoothing function on the top, alpha. So what I'm doing is I'm taking the same build amount and taking the EWM function. I'm giving alpha equal to 0.7, and then I am setting my minimum periods to 3, and then I am calculating the mean over here, right? So this is the mean, and you can see the output again. What I'm going to do is I'm going to take this output and put it in the main data frame. So here I'm creating a variable in the data frame called exponential smoothing moving average, the window function. The window is 3 length, and zero point 0.7 is the smoothing function, so I have given 7, and I've given the same function that I ran on top. I'm doing a shift of 1. Let me run this and let me run the data frame. In the data frame, now you are seeing an additional value over here. Yeah, expo, that is the ESM window 37, and let us like see how it performs. Like, let's take maybe this value. So here it's 86, and here it's 102, 96, 105. This is 90. This is closer to 86. And similarly, like if you see 122, maybe this far off, right? So there are points where it may be a closer. There are points where it will be farther, right? But let's see overall. Finally, when we evaluate how it performs, let us quickly plot it. That's the easy way to check rather than going to each and every data point. So if you see the plot over here, I'm not plotting everything now. I'm plotting only these two variables. The reason is, if I plot it, the plot will look too cumbersome to really visualize it. So if you see the output over here, the blue line is your actual build amount. This is your exponential smoothing moving average. And you can see this exponential smoothing average is able to capture trend in your data. If you see over here, it's able to capture the ups and downs. It is closely following the output, but still there is some error, right? There is maybe a lag that it calculates. There is some error. Now, what you can also do is you can plot everything together and see how it performs. But let's just hold on once I go into the evaluation stage. Sorry. So this is how it looks like. As I said, we cannot see the output properly, but let's the final. I want to talk one more parameter alpha with lesser value in the exponential smoothing average. So it's the same thing that I did on the top. Instead of zero point 0.7, I'm giving zero point 0.3 over here. So as I said, the lower the alpha value, you are weighting your historical functions, historical data more compared to the current data. So I'm giving an alpha of zero point 0.3. I'm doing same as above. I'm running this. I am creating a variable over here, which earlier it was 3 I underscore 7. Zero point 0.7 was the smoothing function. Now it's zero point 0.3. So it's 3 underscore 3. The same function alpha zero point 0.3 I ran. I'm doing shift 1. Let us quickly see the output. This in the data frame now. But the best way is to visualize it rather than going to the data frame. So now if you see over here, if you see, zero point 0.7 was able to capture the variations better than zero point 0.3, but zero point 0.3 is more smooth because it takes historical observation into also consideration by weighing them more. Now this function in the alpha value, lower alpha value, is a nice way when you want to basically smooth your data set, like when your data has a lot of fluctuation, there are a lot of like trends, maybe you want to smooth it out, you can use the lower alpha factor in this case. But this is the output. Maybe it's not performing better as a model, but this is, I just want to show lower value of alpha, and you may need it sometime, like when you are when you want to like flatten the time, flatten the data set better so that you can move it outside. So let me print all the two now, not everything, like only the zero point 0.7 and zero point 0.3 alpha. So you can see the blue is the actual value. Zero point 0.3 is your green one, which is not that close to your build amount, but zero point 0.7 is kind of close to your build amount compared to zero point 0.3. This is the output. Now let me go ahead. I have this all this data in my data frame. If you see in the data frame on the top, I have all this value. You see on the top, I have your moving average, weighted moving average, exponential weighted moving average, exponential smoothing moving average with zero point 0.7 alpha and zero point 0.3 alpha. I'm going to calculate RMSE for each of this, right? So now we know the RMSE formula, right? Basically, it's your y-hat, that's your predicted value, minus your actual value whole square by the number of observations, and then you are basically summing it up and then doing a square root of it, right? So what I'm doing is here from the data frame build amount, I'm taking the from the data frame build underscore 2018 on top, I'm taking the build amount, I am minusing it with the moving average, I am basically squaring it out, I am calculating a mean which is divided by n, and then I am doing again multiplying it by zero point 0.5, which is nothing but your square root function, which is power of zero point 0.5, which is nothing but your square root function, right? So first I am doing by between build amount and moving average. And when I do this between build amount and I'm getting a RMSE of 70.98. Now next I am doing between build amount on weighted moving average. Now between build amount and weighted moving average, the RMSE is 65. You can see the RMSE has got better now. From 70 it has come to 65. The error is basically decreasing, right? Now let me do this with the exponential weighted moving average, right? So exponential moving average, it's 64. It's better than your better than your weighted moving average slightly, right? So it's able to capture your trend better. Now the next one we are doing the smoothing function of zero point 0.7, and when I do a smoothing function of zero point 0.7, you can see it has come to 61 now. So error has further decreased, right? And then finally I'm doing with alpha factor of zero point 0.3, that is a smoothing function zero point 0.3, and it has increased now. It is kind of close to your weighted moving average. So basically, the exponential weighted average and the exponential smoothing function is performing better for this particular data set where there's a lot of fluctuation. Now, the best thing for these kind of data set is to go for more complex models like ARIMA or Prophet or even LSTM if required, right? But in this case, I just wanted to show different moving averages, and moving average has lot of application in machine learning, in data engineering. If you take streaming analytics, as I said, you calculate a lot of window functions. That it's a sliding window function or a moving window function. You have a lot of your machine learning models. Your lot of feature engineering are coming from the concepts of moving averages. But this is about moving average. What I'm going to do is I'm going to go into pure complex model as we go ahead. But I just want to cover more foundational concepts like trend and how to handle trends, how to detrend it before going into more complex models. That's about it. Thank you very much.